And if you approach that golden 20% mark, people really start to raise their eyebrows because it looks like you're making weapons-grade uranium.
For no real reason. It's time for some more of Dr. Ben Miles. Specifically, a $10 billion problem. The inconvenient truth about small modular reactors. Not sure why it's in a cave. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
It feels like everyone on the planet is building their own nuclear reactor company at the moment.
Small plant, very easy, very safe.
SMRs are the future.
This is real and it's happening right now.
The six-pack of small nuclear reactors.
But are we really entering the golden age of fun-sized fission? Well, if you ask me, maybe not.
So it does seem like there's a lot of reactor companies, at least on paper. That's actually not new. There was the Atoms for Peace back in the 1950s, the fast breeder hype train back in the 1970s, and then the Generation 4 nuclear renaissance of the early 2000s, right before I went off to college. But the point is, what really matters is how many actually survive the licensing process, supply chain, financing, and pouring first concrete. And SMRs are not unique here. Any capital-intensive energy tech, which that's what nuclear is, goes through this phase. Solar did, wind did, gas turbines did. Nuclear, in this case, gets singled out because its failures are more visible and larger in magnitude, both more expensive and more energy production we're talking. And as far as the sound bites on small, easy, and safe. Small does not mean easy, does not mean cheap, and does not mean automatically better. What SMR is actually optimized for is risk distribution, financing flexibility, grid compatibility, and deployment options. They're not trying to beat large nuclear on raw thermodynamics. They're trying to solve a different problem.
The majority of the 20th century, we built nuclear power around very large reactors. These plants were engineering giants, typically producing 1,000 to 1,600 megawatts of electricity, designed to supply power to entire regions.
And with that in mind, the actual reactor's thermal output, at least at the plant that I worked at, was upwards of 3,850 megawatts. And that one made about 1,400 megawatts of electricity on a good day.
They worked, but they came with some serious drawbacks. Gigawatt-scale nuclear power plants often cost more than $10 billion and can take a decade or longer to build, looking at
They cost that much in Western regulatory environments that frankly forgot how to build them. It's less a physics and engineering problem and more of a project management, regulatory churn, and highly customized construction failure. Contrast to France that developed a standard design and built large reactors on time and on budget with political continuity. The UAE has also had some better recent results with that.
Hinkley Point C.
That one, $10 billion is a pretty big underestimate for that one. That Hinkley Point C, yeah, that's a money pit.
Makes sense if governments can commit to long-term planning, political stability, and consistent funding, which historically has
that was well timed.
Been a little bit optimistic. Small modular reactors, or SMRs, aimed to flip that model. A typical SMR produces around 300 megawatts, tiny compared to traditional plants, but still enough to power over 100,000 homes.
That's actually at the high end of thermal, so really you should be comparing 300 megawatts to 3,000 to 4,000 megawatts, because the 1,600 megawatts is the high end for electric output.
They are designed to be manufactured in factories, shipped by truck or barge, and assembled on site like nuclear Lego.
Nuclear Lego. All right, so SMRs. You can modularize reactor vessels, steam generators, and the reactor internals, the reactor containment internals within the vessel. So all the things that, say, the control rods connect to, that sort of thing. You cannot modularize site civil work, security, emergency planning zones, grid interconnections, and the licensing effort. So they're going to reduce some costs, potentially, assuming all of this gets fully optimized and operationalized. But they're not going to completely delete the regulatory rulebook especially. Though I will say earlier, he mentioned 300 megawatt SMRs powering 100,000 homes. 100,000 homes. It's actually conservative if you're comparing it to other modular designs like solar and wind, because at a 90% capacity factor, and that is very conservatively low for nuclear, should be upwards of 95, that's going to produce more annual energy than a gigawatt of solar or 800 megawatts of wind, because they have low capacity factors, and that's going to hurt throughout the year. But the real killer here, as far as the nuclear Lego thing, it's going to be all the customized concrete and one-off construction sequences. One potential use for SMRs could be repowering coal power plants, assuming things like turbine compatibility, but that could potentially save you some cost there. Again, not all of it, but it could potentially save you some of that.
Building lots of identical units, the theory was that the cost per reactor drops dramatically. Some developers even claim deployment timelines of just 2
That's the idea, learning curves. Just like producing anything else in a factory.
2 to 3 years once mass production begins. That sounds good in theory, but when you're looking at what's actually happened so far, that promise hasn't really materialized. The clearest example is NuScale in the United States. This was the most advanced SMR project in the Western world.
Yes, NuScale, the big SMR punching bag.
Backed by the US government and approved by nuclear regulators. When it was announced, NuScale claimed it could deliver electricity for around $55 per megawatt hour and have reactors open by the mid-2020s. But as
that's actually not even that cheap when you compare it to large-scale nuclear. But again, you're talking first of kind, that's not terrible.
the design matured, costs climbed and projected electricity prices rose to nearly $90 per megawatt hour before financing, and the total cost ballooned to more than $9 billion for a relatively small plant. Finally, in November of 2023, the entire project was cancelled.
Yeah. Look, all that information's accurate. Man, that was painful. NuScale was very much overregulated relative to the actual risk involved, which tells you something about trying to do anything new with nuclear these days. It was forced into a multi-module turbine island, in that case of that $9 billion project, and had just a nasty, nasty financing structure. But yeah, first-of-a-kind costs, an inflation spike on things like steel, labor, and interest rates. But I will say, by itself, that doesn't mean SMRs don't work. It just means that bad financing, nasty inflation, and first-of-kind project like that doesn't work.
Globally, there are only a handful of SMRs actually operating, and they don't paint a flattering picture. Russia's floating nuclear plant, academic Lomonosov, is often cited as proof that SMRs work, but construction began in 2007 and the plant didn't enter service until 2020. And estimates still put its cost as several $1 billion for just a 70 megawatt reactor, making it one of the most expensive nuclear plants ever built on a per megawatt basis.
That's true, but some context is needed here. This is a barge. It's hardened for Arctic conditions, designed for remote heat and power, so it's kind of a dual role as a heater and a electricity provider. Not to mention, this is Russia, so a lot of sanctions are at work here, adding to the cost. So if you're going to compare this to grid-connected land-based plants, you're going to be comparing a nuclear icebreaker boat to a combined cycle gas turbine plant in Texas where electricity is cheap. Similar physics, thing that provides heat and electricity, but a totally different mission statement.
It works, but it also directly contradicts the claim that smaller reactors are inherently cheaper.
Or you can argue that it means building stuff in the Arctic is more expensive. Come on.
And China's experience tells a similar story. Its ACP-100 SMR began construction in 2021 and was originally expected to come online in 2025. That timeline has already come and gone, and this is happening in a country with state-controlled nuclear industry, central planning, and established supply chain. That is about as favorable an environment as SMRs could possibly hope for.
So China's nuclear industry prioritizes large standardized build, basically what France did in the 1970s. And China's thoughts on SMRs is they're largely demonstration, proof of concept projects, and they're actually not rushing these first-of-a-kind units because they just have different priorities. So I don't know if that's evidence of a systemic failure here. And you could argue that the fact that they're still building the thing is evidence that it is potentially viable. But using first of kinds as proof that SMRs don't work would be a bit like canceling airplanes entirely back in 1912 just because engines kept failing.
The big problems behind SMRs is that they rely on the assumption that things keep behaving the same as you scale them down. But economics and also, I guess, physics both have something to
Nah, they only don't work if you break out the blue Koopa shell.
say about that. The issues being faced by nearly all global SMR projects aren't just the teething problems that you'd expect when creating a new technology, but it boils down to a more fundamental set of problems.
The goggles do nothing.
Oh my.
You might have heard me express a mild level of disappointment. At the end of the day, a lot of the clever fission and even fusion reactor designs coming out are just increasingly complicated ways to boil water, and that the
Yes. That's really not an insult, it's just thermodynamics.
steam engine that they rely on ultimately hasn't really evolved since the 1800s. Now that sounds like a bit of a flippant remark, but it's actually kind of a huge problem. Regardless of how clever the reactor is, ultimately what a lot of the nuclear reactors are at their core, no pun intended, are devices that produce heat, then pump that heat into a heat exchanger in order to boil water, produce steam and power a turbine to generate electricity. That steam is then cooled, condenses down back into water, and the whole thing goes round again in a process called the Rankine cycle, named
Yeah, that's true. Every heat engine is going to be Carnot limited. Think of the Carnot cycle as the idealized version of the Rankine cycle.
after William Rankine, a 19th century engineer
He wasn't a nuclear wizard. It was just steam cycle. If anything, I would call him the balance of plant side wizard. That is to say, the turbine steam cycle.
and strong contender for the most intense beard in human history. The efficiency of that process is fundamentally limited by the temperature difference between the hot source and the cold sink. The efficiency follows the Carnot
Sauce, really? Okay.
relationship of 1 minus the ratio of the cold temperature to the hot temperature. So the bigger the temperature difference, the more efficiently your heat turns into electricity.
And that's why your efficiency goes up in the wintertime, because T-cold gets more colder. The other option is to make your reactors hotter.
Problem number one, and it's a big one, is pretty much every design, whether it's for large nuclear or new small modular reactors, uses the same steam turbine generator as a way of converting heat into electricity. And using this architecture has a fundamental flaw: how hot it can actually operate. To keep the water only boiling where you actually want it and not boiling where you don't want it, pressures in the pipework need to be incredibly high. This places the reactor vessel, piping, and heat exchangers under constant mechanical stress. And even though it is well below the melting temperatures, sustained operation above roughly 280 to 320 degrees Celsius causes permanent damage in shape or length called creep, as well as the long-term weakening that occurs in steels and alloys exposed to neutron radiation. Because these components are safety critical and they're expected to operate for 60 plus years, their allowable temperature is capped conservatively, usually below 300 degrees C. This limits the practical thermal efficiency of the steam turbine to about 30 to 35%. But there's another important, less talked about reason for the general limit, which is that if we go any higher, we start to approach the critical point of water, which is about 374 degrees C at 22 megapascals.
So all of this he's saying is accurate, and there's a few other reasons why you keep things well out of tolerance, or well within tolerance bands. There's also corrosion over time. In the primary systems, you have neutron embrittlement. But I don't see what any of this has to do with SMRs or why they're failing relative to either big nuclear or other modular ways of producing electricity.
Beyond this, water exists in both a liquid and a gas state at the same time.
Yeah, supercritical fluid.
Reducing its ability to generate the pressure needed to drive the turbines. This places a strict limit on the efficiency even if the material constraints weren't a problem. However, although it's rare, this has worked for large nuclear in the past. But why will this not be true if we take this same approach for
And there's also other ways to fully a more efficient Rankine cycle, and that is moisture separator reheaters. You take some of the steam out of some of the stages of the turbine, send it down to feed water heaters, and then heat up your cold condensed feed water before it goes into its interface with the reactor. So overall, your temperature cycle is more efficient. Your Rankine cycle is more efficient. But I'm not sure what the comparison is.
small modular reactors.
Just how is nuclear energy turned into electricity?
That's
So how is this a problem as far as this comparison is concerned? the 30 to 35% efficiency is not the problem. You get similar efficiencies in, say, natural gas or coal. What's going to matter, what does matter is capacity factors north of 95%. And that is where nuclear beats almost everything else. So you take this same 30 to 35% that exists in any thermal plant, and you multiply it by a 95%. Natural gas is a capacity factor of maybe 60% and coal of about 40%. That is the real difference here. Whereas SMRs and large-scale nuclear, it's going to be about the same. Another factor is fuel costs. Nuclear fuel cost is about 5 to 10% of the levelized cost of electricity. Nuclear also beats them in terms of reliability and overall system value. The big disadvantage that nuclear has in general is the high upfront capital cost, but the operational costs are far lower. So this efficiency thing is a wash between everything that uses a steam cycle, and SMRs and large pressurized water reactors still have the same metallurgical limits that he was already talking about.
30 to 35% figure is a conversion efficiency, and it in of itself isn't really a showstopper. What we actually care about.
Okay, so point one as a problem wasn't really a problem. Okay.
Is how much absolute power we can get out of the other end. And at huge scales, reactors compensate for mediocre efficiency by operating at enormous thermal powers. If we have only 33% efficiency, a 3,000 megawatt reactor is generating 1,000 megawatts of electricity continuously, day and night, which is useful on a societal scale, even with high upfront plant costs. And it becomes economical because we cram as much thermal power as possible behind one big semi-efficient turbine island, spreading the balance of plant costs over lots of megawatts generated. And on a levelized cost basis, new large nuclear projects typically fall in the range of $80 to $120 per megawatt hour. That's higher than things like offshore wind at roughly $30 to $60 per megawatt hour, and utility scale solar about $25 to $50, but it is broadly comparable to offshore wind at $70 to $120 and gas-fired power at $45 to $75, once fuel price volatility and carbon costs are included. But back to where we started this conversation, the problem with deploying large nuclear is that it is complex and often runs over time and over budget, so never actually gets built in the first place. This is exactly what prompted us to switch to SMRs. But for SMRs, if you shrink the plant, those same systems become disproportionately expensive. In a large reactor, the turbine island might be 500 million to 1 billion. But for an SMR producing 5 times less power, the turbine island might still cost 200 to 400 million, only around 50% cheaper. So proportionally, you end up paying a very high cost for very mediocre thermodynamics, a weird but very accurate phrase that I wish was on a t-shirt, and ultimately means that a lot of the economic logic doesn't quite add up to criticality when you shrink the plant down.
Okay, so that was true for one build, the NuScale fiasco, and all of these highly customized builds. But if you take into the same consideration that, say, wind and solar had, with the serial deployment, learning curves, fleet economics, economies of scale, then that could make a difference. Wind dropped 70%, solar dropped 90%, gas turbines dropped 50%. Nuclear has been too stop-start in terms of progress that these curves have not been realized. Hence the unfavorable graph that he showed earlier.
Even if you're able to modularize a reproducible reactor. This is why many SMR projects today are quoting a more realistic LCOE in the region of 90 to 150 megawatt hour range, more expensive than large nuclear projects, with the future promise of it will come down at some point due to learning costs.
And that's not unrealistic. So small modular reactors have the potential to have the price come down faster than large reactors just because their duty cycle is shorter. I mean, that's why solar was able to get cheaper, is because it doesn't take much to build one of those things. It's the same logic.
The damper maybe on these sorts of projects is that most SMR designs prioritize passive safety features like natural circulation and gravity-driven cooling to avoid active pumping systems that require human intervention and might fail when you really don't want them to. Those systems place even tighter limits on the operating pressure and temperature, which pushes the efficiency below the already fairly depressing 35% ceiling of water-cooled reactors.
Yeah, that was an active design choice. SMRs deliberately trade some efficiency for much lower accident risk, lower emergency planning, reduced staffing, and insurance and licensing benefits. This was part of the disconnect with the regulator in that their requirements should not have been nearly as strict because of this added design margin, and that is where they would have saved it with those capital costs, planning costs, simple interactions with the emergency planning system, simplifying that a lot more compared to large-scale nuclear plants. Efficiency is not the only axis that matters, even if you're just talking cost comparison.
As I look at the current set of designs for SMR projects out there in the world, it is almost as if we forgot why we built nuclear so large in the first place.
Or SMRs remember why large nuclear has failed. Big reactors failed because they require political continuity, massive upfront capital, and they were easy to cancel mid-build. SMRs are designed to survive this, not optimize your Carnot efficiency. And back in the day, when nuclear was built large in bulk, grids were centralized, financing was state-backed, and demand growth was predictable. Those assumptions no longer hold.
And that's before we even get to the physics.
Go big or go home.
There is another under-discussed complication for small modular reactors. Shrinking the reactor down makes it harder to sustain fission using conventional nuclear fuels. In large reactors, the sheer size of the
More
core
leakage.
helps neutrons stay inside the reactive material environment long enough to collide with fuel and trigger more fission events. When you make the core smaller, neutrons can more easily end up just embedding themselves in the reactor sidewalls, ending the critical reaction. This effect is
Or just passing through, but I get what he means, less overall fissions.
called geometric neutron leakage, and as the reactor core gets smaller, its volume reduces at a faster rate than the surface area, making neutron leakage more likely. In order to compensate for these losses, SMR designers often need to use higher enriched fuels, increasing the concentration of uranium-235 beyond the normal 3 to 5% used in most normal large reactors to between 5% and just under 20%. These are called HALEU fuels, and this puts more reactive material back in a smaller volume and helps keep the reactor critical and allowing for longer fuel cycles. But it also introduces new problems. HALEU isn't widely available yet. It has a much more limited supply chain and requires stricter security licensing and handling than conventional fuels.
It's a weird midpoint because naval reactors are higher enrichment than that, but civilian reactors are not. So, and part of the reason why we don't have the supply for it is there hasn't been much of a demand for mass-producing small modular reactors that require it. This is just like during the Manhattan Project, where the little boy uranium-235 weapon had over 90% of the world's supply of uranium-235, because we didn't use it for anything else back then.
For kind of obvious reason. You're basically at this point making enriched uranium, which most governments of the world frown on.
It's not weapons grade. Weapons grade is north of 90%. The real bottleneck here is going to be the enrichment infrastructure, and unfortunately the political squeamishness with people not actually knowing what this is relative to current civilian nuclear designs and current weapons designs. So it's more of a policy problem than an actual physics dead end.
Fuel enriched above 5% crosses into a category that raises non-proliferation and export control concerns.
It does, but it shouldn't. The physics just doesn't make sense. You can't make a nuclear weapon with 20% enriched uranium. It's just not going to work.
Complicating international deployment. And if you approach that golden 20% mark, people really start to raise their eyebrows because it looks like you're making weapons grade uranium.
For no real reason, but that's only because it's weird because making SMRs like this has not been standardized. So people automatically assume you're going to make a weapon if you get higher than that. It's kind of circular logic.
At the same time as this, the infrastructure to actually produce HALEU at scale barely exists outside of a few countries. So while smaller reactors sound simpler, they quietly push designers towards more complex fuel strategies, and in many cases, SMRs are trading mechanical simplicity for fuel complexity. And that fuel bottleneck is now one of the biggest practical barriers to turning SMR concepts into real deployable power plants.
So here's the thing. HALEU uranium is not required in every SMR case. You're mixing things like other design enhancements, like optimizing reflectors so less neutrons escape, spectral hardening, adding more burnable absorbers to create a more even neutron flux distribution, and further optimizing your fuel geometry without enriching. And this is all assuming you're sticking with uranium and using light water reactor SMRs. You could also use thorium. So this problem is not a universal SMR problem. It's a temporary infrastructure problem. And weapons grade does not start until you get to 90%. He's absolutely right about the political concerns, and people are going to be concerned about any new reactor design that has above what they think is typical civilian nuclear.
It is solvable with scale-up time and policy change, but it's definitely a barrier. So with this problem to face, what do you actually end up doing as an SMR company?
Now, tell them how to run a nuclear plant.
What I'm seeing at the moment is you're really left with one of two options. You can combine many SMRs around a central steam turbine called a multi-modular small modular reactor, what a mouthful, but this means that in principle we've moved from supposedly cheap factory reproducible reactors to once again building large semi-bespoke nuclear facilities. This was the exact story in the...
Yeah, basically getting a six-pack of reactors, and it's the rest of the facility, though, in this case, not the reactor itself, that's going to be driving up your costs.
A cancelled project by NuScale Power in Idaho that planned multiple small reactors.
Yes, they were forced into this weirdo design right from the start. Though, even with this, the reactor modules are still standardized, and outages do not zero out the site or half out the site in the case of the power plant that I worked at with 2 reactors. You can stagger all your outages, and you can have a 6-pack of SMRs, and you could just have an outage for 1 or 2 reactors at a time. And the power plant is still producing electricity. Not to mention less points of failure, so if one reactor trip on a 6-unit site is less significant than a reactor trip on a 1 or 2 unit site.
Feeding into a single shared turbine island. Also, if we take this design approach, we introduce the new problem of getting these reactor modules to operate with compatible pressures, flow rates, and energy exchanges. So projects require additional complex systems and engineering overheads that may be more than anyone actually signed up for.
That would be easier than large-scale, possibly different designs, though, because again, they're all the same design. I'm not sure what he means by that.
The other approach that I'm seeing these companies take, which maybe conflicts with the outward facade of this power is being generated for the people, is that you move your commercial strategy to better take into account the small-scale reactor systems that you're designing. Selling SMRs into niches where electricity prices are not the primary constraint, something like remote grids or islands or mining operations or...
Yes, or that Russian boat he mentioned earlier. That's why it was most expensive. It had a very specific use. And yeah, some of these remote areas, $150 per megawatt hour, that's not that expensive because some of them already pay $300 per megawatt hour, depending on where they are, if they're in like a remote Arctic region or something. And it's all about reliability over price. So yes, this part makes the most sense for what SMRs are starting out as, and hey, it's where we already see some SMRs. And this very concept has existed in the military for quite some time.
Military bases, where at the moment these sites rely on diesel or imported fuels. In these contexts, electricity is already well over $100 per megawatt hour, so SMRs can be competitive despite higher generation costs, while also offering fuel security and lower emissions.
If anything, this right here proves that SMR works. This is the target market to start with, and then as your learning curve matures, you get better at making them, then you can enter markets once the cost goes down where you become more competitive.
If that's something the military decides to care about. You might also try and bundle electricity with other value streams, like combined heat and power systems, supplying not just electricity, but also industrial process heat, district heating, or hydrogen production. But here again, your steam engine design is a
This is kind of counter when he beat up on that Russian boat. I mean, that's what it's doing.
massive limitation. You are capped at about 300 degrees C, which sounds hot, but is actually referred to within industry as low temperature heat, and isn't useful for most industry processes. These fundamentals limit the current SMR designs that are coming to the market to actually making that much of an impact in the common electricity market.
Okay, so 300 degree Celsius heat, that's perfect for things like district heating, desalination, hydrogen via electrolysis. I mean, I know it's not making steel type of heat, but to say 300 degrees isn't useful, I don't know where he's getting that one from.
And us, the consumer, which I think is the one that was actually excited about this all along. The first generation of these SMRs aren't going to be the silver bullet to the energy crisis that we all have assumed that they were billed as.
No one seriously assumed that. They were never intended to replace large-scale nuclear.
So the big question on everybody's mind is, what do you actually do about it? I think there are two things that would materially move the world in the right direction. Number one, if a country committed to building tens or maybe hundreds of the exact same small modular reactor design, I think you would get meaningful benefits from economies of scale and cost of learning reductions that would materially reduce the cost of rolling out this technology. However, you will always be limited by the fundamental physics that is the steam engine.
Yes, which is more efficient than, say, a solar panel or a wind turbine.
I think option number two is kind of more interesting to me. You finally, as the human race, take the bold move and step away from finding increasingly complicated ways to boil water, and instead use a different technology to turn the heat of a nuclear reaction into electricity. Now, there are some options out there already bubbling the periphery, no pun intended, which I think are pretty interesting to look at, but beyond the scope of today's video. But
Alright, so if we're gonna do this, then we've just eliminated coal, natural gas, including combined cycle, biomass, geothermal, concentrated solar thermal, all types of nuclear, and hydrogen power concepts. Climate, grid stability, energy security do not care if your electrons come from steam, helium, supercritical carbon dioxide, or unicorn magic. They care when they arrive, and how reliably. Not saying we should never pursue something that does not make steam, but I don't understand the arguments against it. Is it an aesthetic argument? Does it just feel old? Is it not sexy anymore? I don't know. Let me know in the comments on that one. I've never understood that argument.
thank you, as always, for watching.
So, large nuclear is still essential. SMRs are not cheaper yet, and physics is not your main blocker. It's policy, financing, and continuity. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.